Today, we're tackling a problem that seems simple on the surface, verifying if an array is sorted, but with a twist. It might have been rotated. How can we confirm this efficiently without restoring its original order? Given an array of integers, your task is to return true if the array is sorted in non-decreasing order and then rotated some number of positions. If it's not, return false. An empty array or an array with one element is considered sorted and rotated. The core challenge is to correctly identify a single rotation without false positives. A straightforward but inefficient approach involves trying every possible rotation. For each potential starting point, we'd iterate through the entire array, checking if the elements are in non-decreasing order. If we find any rotation that results in a sorted array, we return true. This means for an array of n elements, we perform n checks, and each check takes n steps. This leads to an overall time complexity of O, n squared. While it uses constant extra space, big O of 1, constant time, its quadratic time complexity makes it unsuitable for larger inputs. The key insight for an optimal solution is realizing that a sorted and rotated array can have at most one break in its non-decreasing order. For example, in 3, 4, 5, 1, 2, the only place where current next is between 5 and 1. If an array is fully sorted, there are 0 breaks. If it's sorted and rotated, there's exactly 1 break. If there are 2 or more breaks, it cannot be a sorted and rotated array. Our algorithm will iterate through the array, comparing each element with its successor. We use the modulo operator to handle the wraparound from the last element to the first. We'll maintain a counter for these breaks. If this counter never exceeds 1, the array fits our criteria. Let's trace this with the example array, 3, 4, 5, 1, 2. We initialize a counter 4 breaks to 0. First, we compare 3 and 4. 3 is not greater than 4, so no break. Next, 4 and 5. Again, no break. Then, 5 and 1. Here, 5 is greater than 1, so we increment our break counter to 1. Moving on, 1 and 2. No break. Finally, we compare the last element, 2, with the first element, 3, using the modulo operator. 2 is not greater than 3. Our loop finishes. The break counter is 1. Since 1 is less than or equal to 1, our condition count equals 1 is true. The algorithm correctly returns true for 3, 4, 5, 1, 2. This is because it represents the sorted array 1, 2, 3, 4, 5 rotated 3 positions to the right, exhibiting exactly 1 break in the sorted order. You'll spot this 1 break pattern whenever you need to check for sortedness in a potentially rotated array. It's also useful in problems involving cyclic arrays or finding minimums in rotated sorted arrays, as the minimum will always be right after the break point. This optimal approach has a time complexity of big O of n because we iterate through the array once. The space complexity is big O of 1, constant time as we only use a single counter variable. This 1 break strategy is a powerful pattern. Try applying it to similar cyclic array problems. Don't forget to like and subscribe for more efficient algorithm breakdowns.